All right. So if you want to confirm whether your system the state space model you guys find is correct, you can just simply do a conversion, which is G as the transfer function equals to this equation. I think Dr. Chen has also taught you that in class, so I won't go through that. And notice that actually the eigenvalues are the poles of the system. So if we consider just the state space, which is x dot t dot xt equals to this. If we find the eigenvalues of this A matrix, we can also find the transfer function of this system. We can find a pose of this system, and you can get the same pose from the transfer function. So if you guys want to design a controller that can stabilize the closed loop, you guys have to make sure that the pose for the closed loop, which is the eigenvalues of this, okay, if we substitute this u here with this minus kt, notice that this u is actually a negative feedback. Okay, so I'm gonna write everything here. So if we substitute that equation, if you guys substitute u with
Nice look.
all right. If you guys substitute u with this k times xt here, you guys will get an equation like this: minus b times u, which is k times xt. And if you factor this xt out, you will get an equation like this, which is a times bk minus bk times xt equal to this. And if you guys want to design a controller that can stabilize this system, you guys have to make sure that the pose for this matrix, all the poses for this matrix are in the left-hand plane. So I think that's basically how you guys can design, the method for you guys to design the controller. And I'll just quickly show you there is something you guys have to notice in the simulation. So for the simulation, some of you might want to, some of you guys asked me how could I load the parameters for the project. I would recommend you guys to write like a MATLAB file, so you guys can load all the parameters here, then run the MATLAB file, and then all the parameters will be automatically loaded into the MATLAB. And this is basically the simulation loop for this for the second plot I showed you guys, which is the a loop for you guys not using the Quasar MATLAB, Quasar software. So this is basically the state space model. You guys can type in the parameters for the matrix here, and the controller part is something you have to worry about, because the system states, like for this lab, there are two system states. So the controller, which is here, for the system should be a matrix as well. In that case, you guys have to change the for sure this game here is not the correct controller, so you guys please do not use this game. You guys have to type in the matrix of the like the controller in a matrix form, and then change this option here to the second one, which is matrix k times u. In that case, you guys won't have the matrix dimension problem. I can show you if you run the simulation with this, you guys are going to have an error of matrix problem. See, that's what I mean by this. So it tells me there's a dimension problem if I'm running this. But if you change that to this thing, the dimension problem will just cancel out. Will just no longer exist. Yeah, and I can get an output from this. Of course, the system state is not correct, so I just show you guys like that's one thing you have to notice, and I didn't write that in the menu, so you guys had to be aware of this. Also, in the project, for the controller part, you have to change the option from the first one to the second one. And some of you might ask, can I do that in another way? Yeah, the answer is this. Since I have the system has two states, I can have two gains here, which the first one corresponds to the theta, and the second one here, which is also like the gain for the theta dot. So you guys can do the controller in another way, but I would suggest you guys use the matrix form for the controller. I think that's pretty much uh, of the tutorial for this lab. And if you guys have any question, I would be here to answer the questions. And some of you might have a question about how can I confirm the file I downloaded from the Blackboard for the project is correct. So here, let's say we have the sorry, it's this one. Here we have the pendulum model, nonlinear model for the pendulum, and if you zoom, like click on the block and change the initial condition here from 0 to 0.1, it's like giving the system a small bias. So the output, you have to disconnect all the feedbacks from the system and just give it a simple output. So if you run this simulation, what you can get with okay, I had to run the other file. All right, so if I run this file, oh, this game here, there's a problem. All right, what you can get from the output, if I have no controller, no other input, what you can get from the output should be something like this. This blue line here represents the rod. If I give it a small BIOS, it will just forward down, and uh, after a while, it stops at the inverted, non-inverted position, which is pi. The inverted position will be 0, which is this. And this this yellow line here represents the angle for the rotatory arm, which is a theta. So if you guys want to confirm whether your nonlinear model is correct, this is a simple way for you guys to confirm. All right, so that's pretty much the thing I want to talk about for the tutorial. And if you guys have any question, I will be here to answer your questions. Yeah, Lab 3 is actually like a warm up for you guys to do the project, because for Lab 3 it's very simple. It just have two system states, and the system equation is a linear system. Unlike the project, the system equation is a non-linear system, and the system states is much more complex than the lab 3. So you guys can do the lab 3 first. After a while, you might get some opinions about how you can derive the state space model, and then do the project. How do I determine K matrices for the project? You mean the controller? Okay, so for that part, it's actually the same. It's actually the same as what I wrote here. So you can use LQR, or you can use pole placement, but no matter which method you are using, you have to make sure that your controller can give you this result. So you have to make sure that the eigenvalues for a minus k a minus bk is actually, which are the poles of the system, are on the left hand plane. So that's this thing, a minus bk or a plus bk. The eigenvalues of this matrix are all negative, which means the poles of the system are on the left hand side. Yeah. You can use LQR or pole placement. There is a function in MATLAB called place. You can try to Google that and see how to use that. Does that answer your question? Yeah. Okay. Any other question regarding to how to design a controller or how to derive the state space model? Oh. Um, I would say both are good methods. It doesn't give you uh like it like depending on which it's actually for LQR, it's kind of similar to pole placement, just depending on uh where your poles are. Like they both, like for both of them, they have the degree of, like they have a freedom to design the controller. They have the freedom to design. So you, depending on where your poles are, you can get almost same results. So I would not say which method is better. They will give you same results. Yeah. It's just like which one is easier for you to use. Yeah. There will be no tutorial, but I think I would be here. Like I would be in the virtual classroom to answer your question. Yeah, you can also email me your question anytime, and I will just reply you as soon as possible. Okay, so what if the eigenvalues are positive? Uh, okay, so I would say for the pendulum, the eigenvalues of the like the uh, eigenvalues for A matrix, which is just the open loop pose for the system without the controller. Uh, like some of the eigenvalues are positive, which means the system, like the pendulum without the controller, is not stable at all. So you have to design the controller in terms of the, like the which is actually the K in the Simulink. You have to design a controller that can make the closed loop pose negative. But for lab 3, probably the eigenvalues for the open loop, just for the A matrix, like the eigenvalues might be all negative. So you just have to design a very simple controllers. But for the project, some of the eigenvalues are positive. That's for sure. Yes, correct. Any other questions? If you have any question, you are welcome to ask, and you are free to leave if there is no question.